This is video 11 from the GCSE Physics video series. This one is on topic 11, forces and pressure. Now, you met the idea of forces and pressure back in topic 6, molecules and matter. So some of this should be familiar, and back then I said to hold it lightly because we hadn't covered pressure properly, but we would cover it later. Well, now is later. So here is lesson number 68. Lesson number 68 on pressure and surfaces. So starting with a definition of pressure. The word pressure has many meanings in the English language, but when we talk about physics, this is what we mean by pressure. The force divided by the area. The force exerted on a surface divided by that surface area. Now, the force must be normal to the plane of the surface area. We're not going to go into what area vectors are at the moment. It becomes slightly complicated. And we do that in A-level. But here we've got a force which is in bold because it's a vector. And here is an area in bold because it is also a vector. And this is a dot product between a force and the reciprocal of the area vector. Now, that is complicated. You don't need to worry about that. What you do need to know is that although force and area are vectors, all we need to know is that we are taking the component of force that is perpendicular to the surface area, the area surface. So this is what this diagram here is trying to indicate. A force normal to a surface, where normal means perpendicular. Fine, okay, we use pascals as the unit of force. 1 pascal is equivalent to 1 Newton per square metre. There are other units of pressure, pounds per square inch, bars, atmospheres, and so on. Well, when we learnt about pressure last time, in video 6, where we learnt about gas pressure, we were talking about the force that particles exert on the walls of a container due to those collisions with the walls of the container. Well, here it's the same idea, but rather than having just particles colliding, we can have anything exerting that force. So we could have someone pushing, or we could have the wheels of this, what is this, some sort of vehicle that's used in making buildings, I don't know what that is, but it's got caterpillar tracks on it, and they are pushing down on the ground. So they're going to be causing a pressure. Or in the use of a scalpel or a lancet or whatever you call this type of instrument in surgery, you're pushing with this instrument upon some sort of tissue in order to cut it. And so there is a force that is being exerted along this edge, this cutting edge. Or when you're walking on the snow wearing snowshoes, your feet are pushing down on the snow. It's a push force. So in order for us to consider maximum pressure, or whatever the pressure is, we have to make sure the force is normal to the area. So we've covered that fine. What does 1 pascal of pressure mean? It's 1 Newton of force per square metre of area. Fine, okay. Well, what does that mean? Well, that means that for a given force, if I make the area bigger, I make a pressure smaller. And that's the idea of these caterpillar tracks. The vehicle is going to be pushing down on the ground, and the ground will be pushing the vehicle back up. And if the vehicle is in equilibrium, then the weight of the vehicle will be equal to the force of the ground pushing up on the vehicle. So the resultant force on the vehicle will be 0. So Newton's third law tells us that the force the vehicle pushes the ground down with is equal to the force the ground pushes the vehicle up with. And Newton's first law tells us that because the vehicle's in equilibrium, then the weight of the vehicle will be equal to the force of the ground pushing up on the vehicle. Hence, the magnitude of the force of the magnitude of the weight of this vehicle will be the same as the magnitude of the force that the vehicle is pushing down on the ground. That's just because the vehicle's in equilibrium. If it was on quicksand, that wouldn't necessarily be the case. But this vehicle's not on quicksand. So we've got the idea that whatever the weight of this vehicle is, that is going to be the same amount of force that the vehicle's pushing the ground down with. Now, if I were to just have 4 wheels on this vehicle, then the contact area with the ground would be very small. So for a given force, which is the same amount of force as the weight of this vehicle, with a small contact area, we'd have a big pressure. And that's going to cause the ground to be squashed more under those wheels, and it's going to cause the vehicle to sink into the ground. So to prevent that happening, we spread that force over a greater area. That is the force that the vehicle is pushing down on the ground with. So not the weight of the vehicle, but it does just happen to be the same as the weight of the vehicle in magnitude and in direction, but it's a different type of force. It's a push force. So this force pushing down on the surface is spread over a greater area, and because of that, bigger area, smaller pressure, so the ground gets squashed less, feeling less pressure. The force is spread over a larger area. Sometimes people refer to this as spreading the weight over a larger area, but that's not quite accurate because we're not interested in the weight, we're interested in the push force on the surface. Or sometimes we do want a high pressure if we want to pierce the skin with our scalpel or our lancet, for example. Lancet, lancet, lancet. Lancet or lancet? I'm going with lancet. So we want a small contact area. And that's why the scalpel or lancet has to be very, very sharp, because that way the area in contact with the skin is going to be very small. And if you've got a very small area, then we have a very big pressure, which is what we need to pierce the skin. So small area for more pressure for cutting with a knife. Fine. Snowshoes, they do the same thing as the caterpillar tracks. They increase the area to decrease the pressure so we don't sink into the snow. And that's it. That's it for our introduction to pressure and surfaces. So let's move on to lesson 69. Lesson 69. We're now looking at pressure in a liquid. And a reminder, you've seen this little bit here before about the difference between rho and P. And back during video 6, when you first met this particular picture with rho is not P in bold letters, you were told that the reason why it's so important to differentiate between these letters is because there will be equations coming up with both a P and a rho in them. Well, now is that time. Here is that equation, and this is how I am writing it. That is not necessarily how you will see the equation written down in textbooks or in other videos from other people, or indeed your teachers or whatever. They might write P for pressure is equal to rho GH. And you can see that's very similar, but I've got some extra features in my equation, such as the bold H and the bold G. We know what that means. If we've watched all the other videos, we'll know bold means that we are dealing with vectors. G, the gravitational field strength, is vertical. H, well, that is a distance, but it's particularly a distance in the vertical direction. It's a height, so that is a vector. It has a direction. And the dot, by now we're becoming familiar with the special use of the dot, means I'm interested in the component of G parallel to H, or perhaps I should say the component of H parallel to G. So I'm looking at these vectors along the same line. If I have my height but I tilt it so now it's a diagonal height, whatever that means, then I'm not. Then I'm going to have to resolve into just the vertical component of that height to do this calculation. So that's the dot and that's the bold. What about the delta? Well, the delta is because this equation, as it's written in red here, that your teacher may give you, is incorrect. What we're looking at is the change in pressure due to a difference in depth of liquid, and actually this works for gases as well, above us. The height of a column of a fluid above us changes our pressure. It adds an extra bit of pressure. Now, the reason why this is important, and I will mention this, we're looking at water pressure, particularly water pressure. So let's look at this shape of this part here, this U tube. It's a tube in the shape of a U. This part here perhaps is sealed, and somehow I have this situation here. Maybe I've increased the temperature of the gas, the air in the sealed part, doesn't matter. Whatever happens, what we've now got is a pressure on this surface and a pressure on this surface. But we've also got the extra bit of pressure caused by this weight of this liquid. Now, the weight of this liquid is going to be equal to the mass of that column of liquid multiplied by G. That's what it is. That's the weight of this particular bit of extra liquid. The density, the mass of that liquid is equal to, let's write that underneath. In fact, let's write these as proper equations because I think this is an important point. Let's use a W for weight. So pen. The weight of the liquid is equal to the mass of the liquid multiplied by G. And I'm only looking at the liquid between these two red lines, this extra height of liquid. The mass of the liquid will be equal to the density of the liquid multiplied by the volume of the liquid. Okay, density equals mass divided by volume, you did in topic 6. So we could say that the weight of the liquid is equal to the mass of the liquid, which is rho multiplied by V. I'm just going to put rho G and then multiplied by V at the end, because this is a weight. Weight is a force. You know, we could replace that with an F if we wanted to. We could replace that with an F if we wanted to. If we divide that by an area, then now we've got a pressure. So force divided by area is a pressure is equal to rho times G times a volume divided by an area. And the area we're interested in is this cross-sectional area of this pipe. That's the area. So the volume of this column of water divided by the area, this cross-sectional area, is going to be equal to the extra bit of height, the difference in height between these two columns of liquid. Okay, A multiplied by delta H will be V. So V divided by A is delta H. But what we haven't done is taken into account the air pressure that's already there. So this is an extra bit of pressure acting on the bottom of this column of liquid. So this is the extra pressure that is experienced at the bottom of this column of liquid here, where my cursor is, this extra pressure just due to the water, the liquid, whatever the liquid is. If you want to know the actual pressure at that point, you would then have to also add the air pressure acting on the top of this surface. And atmospheric pressure is approximately, I'll put P with a subscript ATM to say it's atmospheric, is approximately 101,325 pascals. It depends on the weather. So about 100,000 pascals, which I'd have to add to the pressure caused by the weight of this liquid between the top red line and the bottom red line in order to calculate what the actual pressure is at the bottom. Now, if this bit of liquid in the curved part is not accelerating, then it's being pushed down at the same force on both sides. So that allows us to calculate what the true pressure is on this surface here due to the gas that's contained in here. Now, when I set up this U-tube, originally the two liquids are going to be at the same height, the liquids on both sides of this U-tube. I then sealed the right-hand side and increased the temperature of the that trapped gas. That caused the temperature of the gas. Well, as the gas temperature increased, it increased the pressure of that gas, which caused it to push harder down until the pressure outside equaled the pressure inside. That's what's happening. So this force is going to equal this force. Well, that's fine, but that's only because we've got this extra force pushing down compared to what there was before. So it might be a little bit complicated, it might be a little bit confusing, but that's kind of what's going on there. So the delta P is because we're looking at the extra pressure, the pressure contribution from delta H, this extra bit, this extra depth of fluid, this difference in height. So here's another example over here. We have a container of water and it's got holes drilled into the sides of the container. And you often see this. It's a lovely demonstration. it's full of water, and we can keep the water at a constant height by perhaps having water trickling in the whole time. That's a common way of doing this, to keep the water at a constant height. Well, the water's coming out, but it's coming out faster through the hole at the bottom than it is through the hole at the top. And that's why the water coming out the hole at the bottom ends up farther away from the container, because the water's ejected faster. Well, why is that? Well, it's because it's being pushed harder. It experiences a greater force pushing it out of this hole. Why is that? Because if these holes are all the same cross-sectional area, then the pressure of the liquid behind the water at the bottom is higher than the pressure at the top. But how much higher? Well, we can use the depth of the water, the difference in depth of water between those two holes, delta H, to work out what the extra pressure is, delta P, at the bottom. We'd still have to add 100,000 pascals, 101,325 pascals onto it to work out what the actual pressure is. But just in terms of difference in pressure, that's how we can calculate it. Oh, apologies. Carry on. The water at the same depth has the same pressure. That's because there is the same air above it pushing down, and at the bottom, if there were water, let's imagine this bit of water here was full, then the pressure at the bottom here would be higher than the pressure at the bottom here, which means liquid would flow along in this direction until the pressures were the same. So that would cause this liquid in the right, this liquid level to drop, and the other liquid levels to rise. So if you have liquid that's connected all the way along here, then they're always going to be at the same water level along the top, regardless of the interesting shape of the container. So water, it says here, flows until the pressure is the same along the bottoms, which means that the fluid level at the top must be the same, because we're only interested in the height. We're not interested in anything else, just the height. So it's a vector. And a fluid, I'm talking about liquids, but this all works for gases as well. A question I often ask sixth formers quite early on in A-level is to calculate the depth of the atmosphere. Easy to do. You use the pressure because of the air above us, 101,325 pascals equals what's the density of the air multiplied by G multiplied by the depth of the atmosphere. Well, if the depth of the atmosphere is what we want to calculate, we can use the air pressure, which around the air density, which around here is about 1.2 kilograms per cubic meter. And we could use G, 9.8, roughly what it is on the surface. Or at A level, we use 9.81 newtons per kilogram. And you plug all those numbers in, you get a depth of atmosphere that is way too shallow. And then we can have a discussion about why that is, and it's because rho isn't constant and G isn't constant, and so this equation is far too basic, and actually what you've got to do is change these deltas into D's and integrate. Because rho and G are functions of H, we have to actually do calculus, which is beyond GCSE level physics, so we're not going to talk about that during this lesson 69. So let's move on to lesson 70. Lesson 70. We're back to gas pressure again. Atmospheric pressure. It's come up again. Don't know why, but we're going to do some more detail. So here we have our animation showing the cause of gas pressure. Atmospheric pressure is an example of gas pressure. The atmosphere consists of particles of gas which are moving around and bouncing around, and when they collide with the walls of the container, what happens? Well, the particles change direction. Have a look at these gas particles, and when they collide with the walls of the container, you can see that they change direction. But the change in momentum of those particles is only normal to the surface that they collide. So if they are, let's just follow a particle that's moving along this path, it doesn't change its horizontal momentum. As it travels up, collides with the walls of the container, it doesn't change its horizontal momentum. It's only its vertical momentum that changes. Only the component of momentum normal to the surface changes, which is why it's so important to consider forces normal to the surface. So if that particle changes direction, then its momentum has changed, therefore there has been a rate of change of momentum. If there's a change of momentum, it must have happened over a period of time. If there's a rate of change of momentum, then there is a force that the particle experiences from the wall to change its momentum. And so every time a particle collides with the wall, the particle is pushed by the wall normal to the wall. And if the wall pushes the particle, then the particle also pushes the wall. And that's what's going to cause our pressure. We have lots of particles. This is nowhere near enough particles to really tell us what's going on in the air. We have lots of particles colliding with the wall. So we can average those forces over a small period of time. We can average what those collisions, the force that those collisions are causing, and that becomes our F. The A is just the area of the surface that the particles are colliding with. A. Pressure is a scalar. It just tells us if we multiplied the pressure by the surface area, we would know the magnitude of the force that the particles are causing the surface to experience. Okay, so air particles pushed by surface, so surface pushed by air particles. Newton's third law, I've talked about that. Here's our definition of pressure and the force on a surface, which we can calculate if we know the surface pressure and the surface area. The pressure of the fluid in the surface area. There's atmospheric pressure there. Fine. Now the thing is, the higher up you go in the atmosphere, the sparser the atmosphere becomes. Now, why is that? Well, it's because the higher up you go, the less atmosphere there is above you pushing down on the atmosphere below. So the weight of the atmosphere is considerable, and the weight of the atmosphere above you is what is causing the pressure on your body. As you go higher up, there's less atmosphere above you, so there's less weight of atmosphere above you, so there's less force acting on you, so the pressure drops. Now, because the pressure drops, remember our gas laws, because the pressure drops, the particles are able to be farther apart. So the density drops as well. So not only does the density drop the higher up you go, gravity also gets weaker. So gravitational field strength drops the higher up you go. Now, on Earth's atmosphere, for the depth of the atmosphere, the value of G does not vary very much from the bottom of the atmosphere to the top of the atmosphere. It really doesn't vary very much at all. But it does vary. Now, the biggest contributor to the lower pressure, higher altitudes is the reduction in density of the atmosphere. And it looks like this. The higher up you go, the lower the atmospheric pressure. It's about 100,000, 101,325 pascals when we have an altitude of 0 kilometers. We end up about half that pressure when we're 5 kilometers up. Now, when we're 10 kilometers up, we're now down to about a quarter of that pressure. 15, we're now on about, where are we? Oh, I need to try and read off this. 12.5 atmospheric, so 12.5, so 0.125, so 12.5% of the atmospheric pressure, and so on. And it drops and drops and drops. And this is an exponential attenuation that we can see here. It's dropping as an exponential attenuation. As it says, less air higher up, fewer collisions with surface per second, so lower pressure. That makes sense. The particles are further apart, so they collide less frequently with the surface. But because the density reduces as altitude increases, that's the reason. And why does the density decrease? Because there's less air above you. Why is there less air above you? Because gravity is pulling all the air down. Gravity exists. So that's all this stuff about atmospheric pressure. Interestingly, the boiling point of a liquid like water, let's take water, the boiling point of water depends on the atmospheric pressure. So with an altitude of 0 kilometers, it's about 100 degrees Celsius. As you increase your altitude, the boiling point reduces. I don't know if it follows the same pattern as this. That would be a very interesting coincidence if the boiling point in degrees Celsius varied with the same numbers as what are on the y-axis here. That would be lovely. I don't know. I'd have to check. But the boiling point of water reduces. So that means you cannot get liquid water to temperatures when you're on the top of Mount Everest, you can't get liquid water to temperatures above 70 degrees Celsius or 60 or something. I can't remember what it is. But you just can't get liquid water above that. The water turns into a gas at temperatures below, well below 100 degrees Celsius. And in comets, where we've got frozen water, amongst other things, on the surface of comets, because they have no atmosphere, they're in a vacuum, so there is no liquid water state. Solid water turns into gaseous water with no liquid state. How do we drink? Well, there's no suck in physics. No such thing as suck. So how do we drink? We place our mouth around a straw, and then you think about it. What are you doing? You're sucking the liquid up. No, you're not. What you're actually doing is removing air from your mouth, or at least reducing the pressure inside your mouth by increasing the volume that that air occupies. If there's a hole in your straw, you cannot draw that liquid up, because the air rushes in as you reduce the pressure inside that cavity. But what would happen inside this cavity, this air that goes up into here? I draw my tongue down, or I pull my cheeks down, whatever it is. As you suck, what are you doing? You're drawing your tongue down in order to make your mouth cavity here, your buccal cavity, larger. That decreases the pressure of this air that's trapped in here. But the air pressure outside hasn't changed. And if the air pressure outside is greater than the air pressure inside, then the liquid is going to be pushed down from the outside up into the straw, and then eventually into your mouth. So you don't suck the liquid up, you just make the air inside your mouth occupy more space, and the atmosphere pushes the liquid on all sides up the straw and into your mouth. That is how we drink. It's important to know that there's no suck in physics. Don't talk about successful collisions. We talked about this back in video 6. Don't talk about successful collisions. What would an unsuccessful collision mean in physics? It doesn't mean anything. Has no relevance. Last lesson in this particular video, all about upthrust and flotation. So we've got the same equations we've been working on here, and a principle that you ought to have learnt in primary school, but not all primary school science is done as well as perhaps it could be. The principle is that objects that are more dense than water will sink in water, and objects that are less dense than water will float in water. And I've kept it kind of general here. Now, why is that? Well, because when you put an object in a liquid, there is going to be an upthrust on the bottom of that object. So this object placed into the water is experiencing a force pushing in all directions. So here's a diagram showing the cube, and if it was fully immersed in the water is pushing in on all directions. Why is that? Because the water contains particles. H2O molecules, which are moving around. It's a liquid, so they're able to flow past each other, and they collide with the surfaces of this block. And then they change direction. So those particles get pushed back from the blocks, and the particles push the block in. So this block experiences forces in. But because the depth of liquid down here is greater than the depth of liquid up here, the pressure caused by that liquid down here is higher. So the force of the collisions of the particles into that block down below is higher than up above. Now, all the forces on the left cancel with all the forces on the right, and all the forces on the front surface cancel with all the forces on the back surface. What doesn't cancel out is the forces on the top surface versus the forces on the bottom surface. And if the forces on the bottom surface are greater than those on the top, which they will be if they're immersing the body in a liquid, then there is a resultant force, or should I say the resultant force of the forces I have drawn here will be up. Add all these force vectors together, you get a resultant force up. And what I haven't included here is an arrow for the weight of the object. The resultant force of the arrows I have drawn we call the upthrust. And if the upthrust is greater than the weight, then the object will accelerate upwards. If the weight is greater than the upthrust, the object will accelerate downwards. So let's have a look at what happens when we drop a block in the liquid. it actually bounces around a bit. Let's watch what happens. So 2 kilogram block, it's a wooden block, I let go, it bounces around. Why is that? Because it's falling, so it's got a velocity downwards, it enters the water. The deeper it goes into the water, the greater the upthrust. Eventually the upthrust is greater than the weight, so it accelerates upwards, but it's still falling downwards. So it slows down, stops, and then starts moving upwards. But as it moves upwards, it's gaining that upwards momentum. Eventually it's moving upwards, and the upthrust becomes equal to the weight because it's in that shallower water. But it's got an upwards velocity, so it carries on moving upwards. And as it continues to move upwards, it's less deep in the water, so the upthrust reduces, and so the weight becomes greater than the upthrust. So it's moving upwards, but accelerating downwards. So it slows down, stops, and then starts to move downwards again. And that's why it oscillates a little bit in the water, as you can see. Now, why does it stop oscillating? Well, it stops oscillating because as it's moving through the liquid, it's pushing the liquid out the way, which is causing an increase in temperature of the liquid. It's a drag force, a frictional force called fluid drag. And that is going to cause kinetic energy store of the block to reduce and the thermal energy store of the surroundings to increase. So eventually the block settles in an equilibrium where the upthrust is equal to the weight. If you pull the block deeper in the water and let go, the upthrust is greater than the weight, it accelerates upwards. Something like this over here, this metal block, I'm not sure what metal it is, I can't remember, probably aluminium or something. This metal block, if I were to drop that in the water, the upthrust does increase the deeper it goes until it's all fully immersed. And when the block is all fully immersed, then the upthrust is what the upthrust is. If that upthrust is less than the weight of the object, which in this case it will be because it's an aluminium block, well, I'm sorry, yes, it is aluminium, it says it over here, then I'm sorry, it's never going to have an upthrust greater than the weight, so it'll always continue to accelerate down until there is an upward force on the object, which it experiences when it hits the bottom of that pool of water. The bottom of that pool of water, the floor, will push up, so that the floor pushing up on the block plus the upthrust on that block will end up equaling the weight of that block when it's sat there stationary and not accelerating at the bottom of the pool. So that's how buoyancy works. Now, you can run through the maths here, and there's some clever stuff you can do. You can work out that if the weight of the water that is displaced will end up equal to the weight of the object if it is floating. So let's have a look at this animation here. This is a 2 kilogram wooden block. So the weight of that object is about 20 newtons. If it's a 2 kilogram block, it's 19.6 newtons. So it's about 20 newtons. The water that's displaced is 2 litres. Look, the original volume of this water in this pool was 100 litres. When the block is happily floating, it's 2 litres. The water is now deeper, it's now 2 litres more. So 2 litres of water is being displaced. The mass of 2 litres of water is 2 kilograms, which is the same as the mass of this block. So the weight of the water that's being displaced is just under 20 newtons, which is the same. So this was Archimedes, supposedly, that figured this out, although I'm not sure Archimedes was just looking at displacement of liquid and how the volume increases. But Archimedes' principle is that the upthrust is equal to the weight of the fluid that's displaced. So, yeah, I don't know what else to tell you. The volume of this block is 5 litres. These two blocks have a volume of 5 litres. Or 5,000 cubic centimetres. And when I drop them both in the water, 5 litres, and push them right under the water, 5 litres of water is displaced. But 5 litres of water being displaced on the right-hand case with the aluminium, that has about 50 newtons of force, just under 50 newtons of force, 49 newtons of force. But the block itself is 13.5 kilograms. So the block itself has a weight of 132.3 newtons. So the block itself is always going to weigh more than all of the water it could possibly displace. So there's always going to be that resultant force downwards while it's when it's fully immersed in the water. I think I've covered everything I need to say here. I will just say one thing at the bottom. Don't say buoyancy. I'm not sure why, but AQA, and so it's possibly the same with other exam boards, they don't like the word buoyancy to describe the force that a body experiences due to this displaced liquid or fluid. They prefer to call it upthrust, so call it upthrust. I think it's because the word buoyancy can have different meanings. Buoyancy could refer to the resultant force. So if you have zero buoyancy, then you are floating, you're neutrally buoyant, so the resultant force is zero. Positive buoyancy means you're accelerating upwards, as is the case with the wood when I pull it deeper under the water. Negative buoyancy, it sinks. So I think it's because of that. It might be that there's no consensus about what the word buoyancy means, whether it means the upthrust or it means the resultant force when something is immersed in a fluid. I don't know. I don't need to know. We're just going to remember the word upthrust and use the word upthrust, and that will make us and the examiner happy. And that is the end of video 11, all about forces and pressure. We are going to have video 12 next time, which is starting the topic of waves, wave properties. If any of this was confusing, do get in contact with me, let me know so I can try and explain it. You can get in the comments and comment about it, and I'm sure I or someone else will answer if I don't notice. But we've also got that weekly term time tuition, interactive tuition, very different to these videos. If you're interested in that, physicswithkeith.com. That's what you want to go to. Right, thank you very much for tuning in. Take care.